Hello everyone, this is Zulkarnain. Today I'm going to solve Laplacian and polar coordinates using Fourier Bessel series in the application of circular membrane. Now we first consider the wave equation. This is the Laplace equation, so I can expand this as this is 2 dimension of space. And then next we want to transform this PDE into the polar coordinates using radius r equal to square root of x squared plus y squared, and the theta is equal to r cos tangent of y over x, where x equal to r cos theta and y equal r sin theta. And now we want to transform this term into the polar coordinates, so we need to find the second derivative u with respect to x and respect to y. For the first derivative u with respect to x, we'll have first derivative of u with respect to r and multiply by r sub x plus u sub theta multiplied by theta sub x. And then we'll find the second derivative u with respect to x and second derivative u with respect to y, and we'll have the Laplace equation, which is second derivative u with respect to x plus second derivative u with respect to y will be equal to second derivative u with respect to r plus 1 over r multiplied by first derivative u with respect to r plus 1 over r squared multiplied by second derivative u with respect to theta. Okay, now we need to know about the circular membrane. So I consider that the circular membrane, if I draw like this, so we consider this membrane is radially symmetric. Okay, this radially symmetrical. This is y, this is x, and this is r is the boundary of radius. Because of radially symmetric, this means that the first derivative of u with respect to theta will be 0, and also for the second derivative u with respect to theta will become 0, so this will become 0. So from this PDE we can rewrite second derivative u with respect to t will be equal to c squared multiplied by u r plus 1 over r u sub r. Okay, and the boundary condition are the first, when r equal to r capital, the boundary, it will become 0 for all t non-negative. And then for initial condition, when t equals 0, we can say that this will be the function of r, so you can write function f of r, and the velocity when t equal to 0, this will be the function g of r. Okay, so this is the problem of the circular membrane. So we need to find the solution of this PDE and using this boundary condition. Okay, now we are using separation of variable. So we let u r t will equal to the function w of r multiplied by function g of t, and then from this term we can substitute to this PDE, and we'll have substitute to PDE, we'll have this, and this will be equal to some constant. I can say that this will be minus k squared, and just for convenience you can pick another values. So from this equation we'll have two PDE, two ODEs. The first one is function of w, and the second is g function, where lambda equal to ck. Okay, so we now try to find the solution of the first ODE. Okay, we are using Bessel equation or Bessel function. Okay, first we need to set s equal kr, and then we want to transform this w with respect to r. Yeah, so we need to know about the w, the first derivative and the second derivative respect to r, because r is depends on s. So using the chain rule, this will be okay, and this first derivative as respect to r will equal to k, so I can write this equal k multiplied by dw over ds. And in the same way we have the second derivative w respect to r will equal to k squared second derivative w respect to s. Okay, and then these two equations, we substitute both these into this first ODE, and then we have k squared, we substitute k squared second derivative w respect to s, and so on. This will become k over s from here. So, and then we can cancel this k squared. We can divide by k squared. So we'll have so this is the Bessel equation. we can recall. Okay, can recall the Bessel's equation. This is the form of Bessel equation. Okay, with this equation, we'll have the solution y of x equal to j sub v x plus y sub v x. This is the Bessel equation of first kind, and this is the Bessel equation. This is the Bessel function of first kind. This is Bessel function of second kind. So when we compare this equation to this, we have this actually the Bessel equation with v equal 0. So the solution, so we have the solution of w s will equal g naught x plus y naught x. But this second kind, it will be infinity, be tend to infinity as x tend to 0. Okay, because this membrane is talk about the finite number, so we leave this. So we have the solution of this ODE will become w of s equal to first kind Bessel function of first kind, and we leave for the second kind. Okay, next we want to know the boundary condition. We use, okay, we are using the boundary condition. When r equal to, this should be function u when r equal to r capital, so it will become wr multiplied by gt equals 0. So this will be that wr will equal 0. Okay, and then we get wr equal to j naught kr, so equal to 0. And then we need to know the behavior of this function. We can draw this. If we draw the function of g naught of s, and this is s, so this will look like this, and this so on. And we have zeros, which is when s equal to alpha 1, which is alpha 2, alpha 3, and so on. So we have the zeros. Kr will equal to alpha m, when m equal to 1, 2, 3, etc. Okay, so we have the solution, or we can say Km equal to alpha m over r. So we have the solution wr equal to g naught, and then this is Km r equal to g naught alpha m over r. Okay, is there something wrong here? I'm sorry, it should be r, letter r, and this should be r. Okay, Okay, we have already got the solution of W. Now we need to find the solution of GT. Where we can find this? Okay, the ODE of G is like this. Okay, it is second order, and when lambda equals 0, we'll have the trivial solution, which is GT will equal 0, and this will affect then that the function of u will also become 0. And when lambda is not equal 0, we'll have the solution GT equal to a m lambda m t plus bm. I'm sorry, this should be cos am cos lambda m t plus bm sine of lambda m t. Okay, and then we have two solutions here, W and G. So we have the solution of u or t will equal to the sum of Wm r, so will be m multiplied by gmt, where m equal 1 to infinity. Okay, so we can expand this for Wm and Gm. So we'll have the multiply by G naught alpha m over r. Okay, and then we need to find the coefficient, which is am and bm. Okay, now we are using the boundary condition, saying boundary condition. So when t equals 0, so u or 0 will equal to the sum of am a sub m g naught alpha m over r. Yeah, so we just substitute this t equals 0, so this will be 1, 0 will be 0. So u r 0 will be am multiplied by g naught. Okay, all right, and this will be equal to fr, as it was stated before in the model of problem. And we are using the Fourier Bessel series. We'll have a sub m equal 2 over r square g1, which is 1 because this is 0. So if this is gi, this will be gi plus 1 square of m multiplied by integral Okay, in the same way we need to find the b sub m. Okay, this is a sub m, we've done it. And then for finding the coefficient b sub m, we need another boundary condition, which is a boundary condition, that is the velocity when t equals 0 will equal gr. Okay, now we have to make the derivation of u respect to t. Have u here, and then we make a derivation of u respect to t. So we have ut equal to minus a sub m lambda m sine lambda m t plus bm lambda m cos lambda m t, and multiply by Bessel function. Okay, and this velocity when t equals 0 will become because this will become 0 and it will become 1. And as we know that lambda sub m equal c km, and this km itself equal to alpha sub m over r. Okay, and this will equal to g r. Okay, so using the Fourier Bessel's series, same with when we find the a sub m, and we have the bm multiplied by, this should be c alpha m over r equal to over r square and the integral so b sub m equal to this will be 2 over c alpha m which is dr. Okay, we've done it. We have solved for the Laplacian unipolar coordinates. This is the solution, and then this when we find the coefficient a sub m, b sub m, we have already found it. This is a sub m and this is b sub m. So thanks for watching. I hope this is beneficial for you, and see you next time.